Historical geology students. This is the second video um, for this week of January the 18th to January the 23rd. I'm going to make another one or two videos more before Monday for you to watch. The previous video was called Spring 1, so this one's going to be called Spring 2. And the previous video we talked about the syllabus. So if you have any questions about the syllabus, let me know. And I'm also going to send you a lab on the metric system, and that's going to be due on Wednesday by 7 p.m. So bottom line is, we want to get started talking a little bit about before we get started, we want to talk a little bit about career opportunities in geology. And rather than use up this video talking about it, I want you to please go to YouTube and type in geology degree, is it worth it, and what do geologists do? And she's going to talk about her experiences in getting a geology degree and the sorts of jobs that are available. So watch that video. Type that in under the search for YouTube, geology degree, is it worth it, what do geologists do? That'll give you an idea as to the sorts of jobs that are available. I'll just say that the jobs that are available are working in a natural resource extraction. That means taking things out of the earth that can be sold for money. And that includes oil, natural gas, coal, uranium, metals like copper and iron, etc., and nickel, platinum, and also your precious metals, platinum, gold, silver. That's a big industry. Removing gemstones like from the earth, like diamonds and rubies and emeralds and opals, etc. And clean water, extracting clean water from the earth to supply the needs of companies, farmers, and the general public. So that's the first kind of job you can do as a geologist, is natural resource extraction, removing things from the earth that can be sold for a profit. The second thing that you can do as a geologist is you can be involved in environmental protection. That means keeping our nation's air and water supply clean. And to do that, you have to enforce, you can either be involved in the enforcement of environmental laws or in the compliance with environmental laws. So if you're in the enforcement side, you work for the government. For the federal government, you'd be working for the EPA, the Environmental Protection Agency. If you were working, you could work for state government, the state of Tennessee, the state of Rhode Island, the state of Nevada, or wherever you are, to enforce state environmental laws. Environmental compliance is you're working for companies to make sure that your company is in compliance with environmental laws, such as the Clean Water Act, the Safe Drinking Water Act, the Marine Protection Research and Sanctuaries Act, the Resource Conservation and Recovery Act, the Comprehensive Environmental Response Compensation and Liability Act. You don't have to memorize those, but basically environmental compliance or environmental enforcement fall under the umbrella of environmental geology. So you can work for natural resources extraction, you can work in environmental geology. The third group of geology jobs involves education. So you can use it if you're going to be a K through 12 teacher to teach geology. You can use it to teach college like I do. You can work for an organization like the National Geographic Society or museums, hire geologists to be curators and also to set up displays for the public. Those are the sorts of things that geologists get involved in. Um, if you want to go into geology, I will help you. I've helped about 20 students over the last 6 years get into geology. I've got connections at the University of Tennessee through a program called Geopaths. And Geopaths is a program that where we recruit people who are you need to get an A in this class. You need to be interested in geology as a career. And let me just show you some of the things that we've done in Geopaths. I'll show you some photographs here. Okay, here we are out in the field, and these two young men here are going to be they're already geologists. This is I don't know if you know this guy is Mr. Bryce Bonilla, really smart guy. Anyway, and this gentleman too. We're looking at soil samples, and so keeping our soils productive so that we can increase farming yields and grow different types of crops. That's another thing geologists do. We spend a lot of time going out into the woods and out in the remote areas to sample rocks or soil or look for fossils. Here you can see a whole bunch of these geopath students, and each of these, and here she's a professor of geology at Pellissippi, and he's a graduate student. But these three are going through geopaths. If you're interested in that, let me know, and I'll do the best I can to help you. You can say, I love this stuff. This is fun to me, going outdoors and camping. Geology is mostly for a person who loves the outdoors. Um, you get to travel a lot if you can learn a foreign language. Uh, pour exemple, français. Je parle français. If you can speak French or you can speak Spanish or Deutsch or German or whatever, it could lead to you going to different countries and working. And you also get to work throughout the United States and Canada. And here you can see we're looking through our samples. These two people here have become good geologists. And it's a lot of fun going at geology. So, if you're interested in geology as a career, let me know by the end of the semester and I will help you. I just love it because to see young people's lives transformed, and you need to find at your age when you're trying to figure out what you want to do with the rest of your life. It's a real hard thing to do. When I was 18 years old, I didn't know what I wanted to do with the rest of my life, and my father suggested I go into accounting. And so I took some accounting classes, and I was bored out of my skull. I knew that's not what I wanted to do for the rest of my life. And so I decided to pick a college major that interested me, and I never regretted it. I love what I do, and I've had great experiences. So I picked geology. I also was an ROTC and so I was I was a forward observer for the Army, which basically means you go out in nowadays you go in Humvees, but back then you went out in a Jeep with three other men, and you would identify enemy targets and call for artillery fire or airstrikes or naval gunfire if you're near the coast, or mortars. So you have to be able to identify the enemy and then give the map coordinates and then call for fire. So I did that for a while, and I used what I learned in the Army in geology because map reading skills are very useful. I spent my 6 years in the Pennsylvania National Guard, and then I decided, well, I really loved being in the Army. I made a lot of good friends, but I decided to go to graduate school instead of continuing on in the Army. Um, anyway, Chapter 1, the dynamic and evolving Earth. So let's get down to nuts and bolts. Uh, you should have a textbook. If you don't have a textbook yet, order one. You need one. All of these PowerPoints that I'm going to do are straight out of your textbook. So get your textbook ordered as soon as possible. Get it from the bookstore if you can at Roane State, and that'll be the fastest way of getting it. Or if you can't get it that way, get it at Amazon.com or eBay or some other website. But make sure you get a textbook. Try to get it this week. It's very important to prepare for the first test, and the first test will not be, let me think, 1, 2, 3, about 3 or 4 weeks from now. So, but in the meantime, you can watch these videos to get the information you need. And my image is somehow frozen, but hopefully you're still seeing this. So the dynamic in evolving Earth. The Earth is constantly evolving. When you see that word evolving, you want to think of changing with time. That's what evolving means. When something changes with time, it's evolving. And the Earth is moving. It's dynamic. It's moving inside of the Earth and on the outside. The continents are moving, believe it or not. North America, for example, is moving east at about 2.5 centimeters a year. That's 1 inch a year. And in science, we like to use the metric system because the rest of the world is using the metric system. We're the only ones who still, basically, we're the only country that still uses the English system. So your first lab is going to be on learning about the metric system, but we'll still use the English system too since it's used in the United States. So we need to know both systems. The Earth is a dynamic planet, and it's continuously changed since its formation 4.6 billion years ago. Write that down. How old is the Earth? 4.6 billion years old. How in God's name do we know that? Well, if you wanted to figure out how old the Earth is, how would you do it? You'd find the oldest rocks on planet Earth, right? And you would use something called radiometric dating. And radiometric dating works, ladies and gentlemen. I've heard different people say different things about radiometric dating and how it's not accurate. It is very accurate, and we're going to radiometric dating. I've used it. Hundreds of thousands of scientists used it. It's reproducible. You always get the same numbers, and it's based on basic chemistry. And without getting into the chemistry part now, because I just wanted to get you introduced into geology, I'll just tell you that the oldest rocks on planet Earth that have been found are about 4 billion years old. So we know that the Earth is at least 4 billion years old. However, we have found little crystals of even older Earth material in younger rocks. Let me explain. If you took physical geology, you might recall that the Earth is made up of rocks. 3 kinds of rocks: igneous, metamorphic, and sedimentary rocks. And rocks are made up of minerals. There are 3,000 known minerals on planet Earth. 3,000, more than 3,000 minerals. So rocks are made up of combinations of different minerals. Well, this mineral, zircon, Zircon, as you can see here, these zircons have been dated and they're 4.4 billion years old. So these tiny blue mineral crystals of zircon, 4.4 billion years old, have been found in younger sedimentary rocks. Rocks that may be 2 billion years old. So bottom line is the Earth must be at least 4.4 billion years old. How do we know that the Earth is 4.6 billion years old? Well, back in your grandparents' generation, we had astronauts landing on the moon. And that was the big thing in the 1960s, man landing on the moon. And they brought these rocks back from the moon, hundreds of samples, and almost all of them are 4.6 billion years old. Now we know that the solar system, including the Earth and all the planets and the sun and the moon, were formed at about the same time. And I'm going to show you why later on as we move on through this chapter. So we also have meteorite samples, chunks of rock that come from outer space, and they're 4.6 billion years old. So we haven't found a single 4.7 billion year old rock as of yet, telling us that the Earth must be is probably about 4.6 billion years old. So three themes run throughout Earth history that we're going to talk about over and over and over again. The first is plate tectonics. The second is organic evolution, also called biological evolution. And the third is geologic or deep time. What are these about? Well, let's first talk about plate tectonics. We have a whole chapter that is about plate tectonics. And plate tectonic theory, it's a scientific theory, is probably the most important scientific theory that you will study in geology. In the past, when you go back into the 1800s and before, people used to believe in this concept known as permanism, Permanism. Permanism was the idea that 19th century scientists used to have, that all of Earth's landforms are permanent and have not changed since its formation. And that the Earth they also used to believe that the Earth is 6,000 years old. Now, this 6,000-year-old Earth and the Earth not changing in those 6,000 years is the idea of permanism. I can tell you that that's absolutely impossible, that the Earth is 6,000 years old. And it's not Christian. It's not a Christian idea. A lot of people say the Bible says the Earth is The Bible does not say the Earth is 6,000 years old. Christians with an education know that that's not possible. That is not from the Bible at all. That is from one man, James Ussher. So James Ussher, Sssher, believed in permanism, and he came up with a theory to say that the Earth was 6,000 years old, and his theory is called Catastrophism. And this idea of catastrophism dominated scientific thought in the 1800s, and the 1700s, and 1600s. Now, who is James Ussher? James Ussher was an archbishop in the Presbyterian Church, and he interpreted the Bible to say the Earth is 6,000 years old. Presbyterian Church is also known as, you probably know, the Church of Scotland. The Anglican Church is the Church of England. Well, you know, we'll talk about. There's no way of talking about it without talking about British history. One of the Tudor kings, Henry VIII, wanted to know how old the Earth was, and he asked the leader of the Scottish Church, the Presbyterian Church, to figure it out, and he said 6,000 years old. The Presbyterian Church no longer teaches that. The Earth, so in the early 20th century, there was a German man, scientist, by the name of Alfred Wegener. And who is Alfred Wegener? Well, Alfred Wegener came up with just a revolutionary new idea called continental drift in 1912. And this was the first step towards modern geological science. And he said, no, Wegener said the Earth, the continents move. And they have been doing so over hundreds of millions or billions of years. We didn't know exactly how old the Earth was back in 1912, but we knew it must be billions of years old. And we'll look at the data, how they got to that point, and knowing that. But basically, the continents move. The Earth's features are not permanent features. They're dynamic. They're evolving. They're changing. And this would eventually lead, in 1962, to two people, Harry Hess and Robert Dietz, coming up with a new theory of plate tectonics in 1962. Harry Hess and Robert Dietz, plate tectonics, 1962. Should be mentioned that Harry Hess and Robert Dietz are from the great state of New Jersey. They're from my home state of New Jersey. So, Harry Hess and Robert Dietz, they are great men. You know what I'm saying? That's the way I used to talk a couple decades ago. But then I moved to Tennessee and my accent changed. But I'd say that Harry Hess and Robert Dietz are great men. You know what I'm saying? Capiche? All right. Anyway, so those are some of the main people you want to remember. The next thing we want to talk about, another theme that's going to run throughout Earth history, is organic evolution or biological evolution. And in order to understand that, we're going to study Charles Darwin and his theory of evolution through natural selection. Okay. The fossil record clearly indicates that species change and that new species can originate from older species. Clearly shows that if you look at the rocks. If you look at the older rocks, humans have changed. If you, dogs have changed, wolves have changed, and new species have arisen from old species. For example, amphibians. The most ancient amphibians evolved from certain types of fish. We have birds evolving from dinosaurs, and this all came from a man named Charles Darwin. When you talk about biological evolution, people twist what Charles Darwin said, and some evil people have used biological evolution to advance racism, like Hitler. But that's not what Charles Darwin is about. Charles Darwin was a Christian. He studied the Bible very carefully. He believed in a creator, and so people twist what he says. Most Christians believe that evolution occurs, and so it doesn't mean that if you believe in evolution, you don't believe in the Bible. That's the first thing that's important to me because I'm a Christian, and if you are a Christian, you could say God created evolution so that his creations could survive. But they clearly have evolved. And we have to study Charles Darwin and DNA to see how species change. And evolution occurs. We see it occur as the coronavirus evolves. We see, unfortunately, and that makes it harder for us to fight it, the coronavirus. We see it with all diseases. We see it with humans. We're changing. We're not the same as we were 10,000 years ago. We're losing our wisdom teeth and our appendix. Our brains are becoming larger. It's clear if you look at the fossil record. And with all species. Dogs. I love my dog out there, and I'm going to have to go feed her after this video. But dogs didn't exist 100,000 years ago. Dogs have evolved from wolves. Our Ice Age ancestors domesticated the meekest and the friendliest wolves and bred them over and over and over again to make a new species, dogs. So humans can create new species, but Charles Darwin was basically interested in nature selecting who gets to survive. If you have what it takes to survive, you pass on your genetic information. That's just common sense if you ask me. For example, in the distant past, we had giraffes with long necks, medium-sized necks, and short necks. There was a drought that occurred, and the leaves were high up on the trees. Who do you think is going to starve to death? Well, the giraffes with medium and short necks couldn't reach the leaves. They died. So the giraffes changed. So they developed longer necks. That's what evolution is about, and we'll talk about that. It's very interesting. Third theme that's going to run throughout this historical geology class is geologic or deep time. So for you and me, 100 years is a long time. It's the year 2021 now. Well, think about how 100 years ago, 1921 it seems like a long time ago. Henry Ford had just come out with the horseless carriage, the Model T. The Great War, World War I, had just ended 2 years previous, and the Spanish flu was still running through the world and killing people. Who was the president of the United States? Warren Harding. And he had a heart attack, and then Calvin Coolidge, the vice president, became president. That was a long time ago to a lot of people. Let's go back even further back, 2,100 years ago, when Christ was walking the planet. That may seem like a long time. The Roman Empire was at its zenith, and so was the Empire of China, and you had barbarians in Germany, and you had various tribes throughout England and Scotland fighting for dominance. That was a long time ago to some people. That's nothing. To geologists, we're talking millions, hundreds of millions, and billions of years ago. That's what deep time is. So to study historical geology, we need to change our concept of time. 100 years, a million is not much time. 10,000 years is not much time. We're talking billions of years of Earth history. The Earth is a system a complex system. And the best analogy I can give for that is the human body. The human body consists of so many different systems. You got your circulatory system that circulates your blood, your muscular system so you can raise your arms and do the things you want to do throughout your day. You have your nervous system, which transmits signals up your spinal column um, through your brain, and so that it commands the various muscular system to know what to do. All these systems in your body work together to make your body work, right? Well, the earth is the same way. It's got these different systems that make the earth healthy and work correctly. And there are four main systems that work together to make a healthy earth, and they are the atmosphere, the biosphere, the hydrosphere, and the lithosphere. Why do they have mantle and core written here? Well, the mantle and core are part of the lithosphere. Okay, so we got four main systems on our planet: the atmosphere, the biosphere, the hydrosphere, and the lithosphere. Sphere means system in Latin. The atmosphere is the first sphere that we want to talk about, and it involves everything above the solid earth. All of those gases that are held close to the earth by Earth's gravity. Earth's gravitational pull holds a cloud of gases around our planet, and including oxygen that allows for animal life. Animals need to breathe oxygen through a process called respiration. It includes all of the clouds that you see. That's the atmosphere. When spacecraft leave our atmosphere, you can see this burning as the spaceship has to, this heat that concentrates on the nose cone of the rocket as we leave the atmosphere and go into outer space. So that's the atmosphere is where our weather occurs. Second sphere that is important for our planet is the biosphere. I think you already know what that is before I even say it. The biosphere is all the living things on planet Earth. We're going to be studying that in historical geology. That's what makes it different than physical geology. The biosphere includes animals, plants, funguses, and protists. What are protists? Those are single-celled creatures, such as bacteria. So we're going to be talking about living things and how living things change over time. In other words, how they evolve, and what types of creatures lived in the past that no longer live today. For example, one of the creatures that we're going to be talking about in this class used to live in Tennessee. There were a lot of them found in around Johnson City, are saber-toothed cats. These saber-toothed cats are an extinct life form, but they don't exist today. But they have been found in fossils. We'll be talking about all kinds of different extinct life forms and what happened to them. The next sphere that interacts to make a healthy Earth is called the hydrosphere. And hydro means water, and that means the water on planet Earth, including oceans. 97% of Earth's water is in the oceans. And then glaciers, that means where water is frozen near the Arctic Circle in northern Canada and northern Russia. Also Antarctica and Greenland. That's where we have ice. It includes all of your rivers and lakes. That's surface water, and includes water under the ground, which is groundwater. That's the hydrosphere. Any place which has water is the hydrosphere. Then the lithosphere. The lithosphere is the solid earth, and then it's all the rocks underneath your feet going all the way to the center of the earth. How far is it to the center of the earth? 6,370 kilometers. Or approximately 4,000 miles. And inside the lithosphere, we've got the crust on the top, and then beneath that, the mantle, and then the core. Here you can see that the four spheres interact with one another. Here's your atmosphere, here's your hydrosphere, your biosphere, and the lithosphere. And they interact with one another to make a healthy planet. They're not separate and on their own. And what causes them to interact with one another is energy within our planet. There is energy within our planet produced by radioactive isotope decay. This natural radioactive decay in the earth produces heat, and that causes interactions between these four spheres. For example, to understand how these different systems in the earth work, think about a coastline, Myrtle Beach. You've got beach sand and the rocks underneath it, that's the lithosphere. You have the waves crashing onto the shoreline, that is the hydrosphere. And then also rain is the hydrosphere, when it rains on the coast. Then you've got all kinds of creatures that live in the sand, like sand crabs and clams and mussels, and then fish in the water. That's the biosphere. And then you have clouds and oxygen above. That's the atmosphere. All of those spheres interact. The clams and the oysters have to breathe. They're animals. So they interact with the atmosphere. They require water or they die and dry out. So they're interacting with the hydrosphere. They need sand to burrow into so they can survive. So they're interacting with the lithosphere. So all four of those have to interact to make a healthy planet and healthy ecosystems. And you could read this out of your book, but all four of these spheres interact to make a healthy ecosystem. We need to protect our planet's resources so that our ecosystems are clean. New species don't go extinct. Humans don't get sick when they go into the water. You don't want to get sick when you take your family to Myrtle Beach. You want them to be healthy. You want our water supply to be clean. You don't have to be a Democrat or Republican to want to go to the Big South Fork and not see garbage thrown out in out in the woods, or motor oil. And you don't have to be a Democrat or Republican to want clean air and clean water. So we need to keep our environment clean, and at the same time, we want our economy to grow so that there are jobs. And that leads to the holy grail for all geologists. Geologists want to have sustainable development. What does that mean? Sustainable development. Sustainable development means extracting natural resources out of the earth to produce economic growth while at the same time protecting the environment. I'll repeat that. Sustainable development is extracting natural resources out of the earth for a profit to promote economic growth while at the same time protecting the environment. That's the holy grail. That's what we're searched for. we want to protect the environment, we want our economy, but we need to take things out of the earth, such as clean water and uranium and iron, so we can build our automobiles, and copper, so wire, and all kinds of things. We need to have a mining industry. You need gasoline in your car. There's all kind of natural gas to heat your house. We have to do that, because otherwise there's no jobs for young people. The economy would crash. But we have to do it in an environmentally responsible way, protect the environment, and we need to have economic growth. We need to be able to do it for a profit. And I believe our system works. And for companies to make a profit is a good thing. It's what generates economic growth. There's nothing wrong with capitalism. That's why socialism doesn't work very well, to tell you the truth. And we can have economic growth and protect the environment at the same time. That's called sustainable development. I'll call it quits from here. I'll make another video soon.